learning how to diagnose heating, air conditioning, and AC. Excuse me. And because this is the second half, we're now going to dedicate this to air conditioning. So, ladies and gentlemen, there's two things that I want to show you. First of all, a lot of the material that we're going to be using was taken out of the Rheem air conditioning training manual. And whether you have this or not, it doesn't make any difference, because we gave you a handout that goes with the video. And let's see how we can do this. I'm going to show you this on the overhead, but this is what the handout looks like, and there might be about 10 pages in there or so. So this will keep us organized. So again, we do want to get started with this. And again, we're going to go through some of the basics here. And we're going to, again, review the basics. And you may think that you might not need the basics, but I got to tell you, in the classes that we've done, we've had some newer technicians and some very experienced technicians who said this was a good refresher. So we're going to show you some things that maybe you have forgotten, if in fact you've been doing this for quite a while. But this all relates to how we can diagnose again in 20 minutes. And also we'll teach you how to fill out a job site sheet. I would like you to take a look, first of all, at page 5 in your handout. And I just want to correspond this with the paper copy that I have up here to make sure we got the right one. And that is not page 5, so just a second. Page 3, please. I'm sorry, page 3. Now, again, this is just a copy of some notes and a chart that I would use during the class, but it will serve the purpose because we're going to be showing you about what happens when a system is not charged correctly. We're going to show you the chart, but I have some handwritten notes down here, and I'd like to discuss these with you because I've got 7 different methods of charging that a lot of the old-timers would teach the new technicians. And I got to tell you, gentlemen, or ladies and gentlemen, these methods never did work. So again, we talk about the first one where we said, well, let's charge residential AC so we have a low side pressure of 68 psi. You know, that's not correct at all under all conditions. It might be only correct under one condition. So to charge it with that method all the time is not correct. We also would teach our younger people to grab the suction line and just continually add gas until the suction line is cold, and of course how cold? Until it's beer can cold. And I've got to tell you, ladies and gentlemen, I have a book at home that actually tells us how to do that. That book goes back, it's probably 35, 40 years old. We also talked about charging. Oh, let me stop there a minute. Let's talk about that charging to beer can cold. We're going to be talking about undercharging systems and overcharging systems and properly charging systems. Just so you understand that in this class we're going to be talking about residential AC and fixed orifices. We know that we have capillary tubes as a metering device, fixed orifices, and expansion valves, thermostatic expansion valves. When you have a capillary tube or a fixed orifice, we want you to understand that the charge is very critical. And we would say it's plus or minus how many ounces. Now again, different people, different methods, and different opinions. In this class, we're going to be talking about critical charges plus or minus 2 ounces. So if in fact the system took 50 ounces of refrigerant as being a residential AC, if it actually took 50 ounces, if you charged it from 48 ounces up to 52 ounces, you would be accurately charged. And that system would last forever. As long as you did an annual PM check and cleaned the condenser and had the proper voltage all the time, that system is designed to last 20 years, but I got to tell you, if it's accurately charged and maintained, it'll last forever, okay? All right, so, I'm sorry, so let's go back to the cold suction line. So when we do charge a system to beer can cold, I have to tell you that those systems are absolutely overcharged, and typically beer can cold is 2 pounds overcharged. 16 ounces equaling 1 pound, okay? Now you know why we have compressors that fail. Let's go back to the other methods. We talk about technicians who say, I'll put my amp probe on there and we'll just charge it to the RLA, the running load amps, and I'll charge it to the compressor amperage. Well, that's not correct either, because running load amps are for 115 degrees. If a technician is putting their amp probe on a system, and it's only 85 or 90 or 95 degrees or 100 degrees, and they stick their amp probe on it, and let's say it says 17 amps, and he charges it until the compressor is up to 17 amps, when in fact it does get hotter, it's grossly overcharged, and that's how we lose a compressor, okay? All right, so we don't want to ever charge by amperage, okay? Some classes, they say, well, charge everything to 30 over ambient. Well, that's when your condensing temperature is 30 degrees over the ambient. Well, I got to tell you that never was true, and it's absolutely not true today. If we sit there and charge a system until the condensing saturation temperature is 30 degrees warmer than the ambient, typically we're going to be overcharged, especially today, because we have high efficiency units. Remember, the high SEER units are very big physically, and the pressures are much lower. Today we could have 25 over ambient. We could have 20 over ambient. We could have 15 over ambient. And I can even show you a chart where it shows 11 over ambient. So if we do charge those to 30 over ambient, again, we are overcharged, okay? All right, so let's go over here. How about if we charge the system, keep adding gas until our temperature difference across the coil is 20 degrees? You don't always have to depend on 20 degrees. You know, what's the latent heat inside the home? You could have high humidity and your temperature drop is not going to be 20. Could be 18, could be 17, and that could be considered normal. So that's not a good method. How about if we just keep charging until the dome of the compressor sweats? Well, again, that never was a good method. And boy, if you try and do that with a scroll compressor today, the scroll dome is your discharge, and that will never sweat. Okay, that's very hot. You can burn your hand on the top of the scroll. Or how about if we charge everything until we get 20 degrees of superheat? Well, that's not true either, ladies and gentlemen, because our superheat varies all over the board, and I'm going to show you that. So keep in mind, I'm going through some methods that didn't work here. We're doing this very quickly, so I'm going to show you some methods that absolutely work perfect. They are so easy today. We're going to make your life so easy with this, and you'll be able to diagnose problems as well. Now, I'd like to go back to this chart and show you this chart. I've been using this forever, for many, many years. And it'll give you an indication of what happens when a system is undercharged and overcharged. It's only a chart. It just gives us an idea of what happens. I'd like you to look at the left-hand side of the chart, where this would be the capacity in BTUs, how many thousands of BTUs. And we're actually going to be talking about a system that might be about a 26,000 BTU unit. We have, on the right-hand side, is the electricity that's being used. This is our kilowatts. And we have two lines. We have a kilowatt line here, and we have a BTU line here. But take a look at the bottoms, because I'm going to ask one of you a question about how much you want to overcharge this and undercharge this in just a minute. But down here is the percent of the charge. Again, only being a chart that we can use as reference, because watch what happens when we undercharge and overcharge. If I say to you, and again, let's just take an example. I'm going to say that there might be a data tag that might have 50 ounces on the tag. And the tag says, and if we compute that, we're saying that we want 50 ounces of refrigerant in there. Well, if I have a 100% charge, I would start my line here and I'd have 50 ounces in there. Okay? And that could be typically, actually today, a charge of a 2.5 or 3 ton system. But we're using this chart that shows a 26,000 BTU air conditioning system. Okay? So if I run my line on the 100% exact charge, if I come up here to the kilowatt line and then run over here to my kilowatt chart, I could say that this system is consuming, what, about 3,200 watts, 3.2 kilowatts, 3,200 watts as it's running. Okay? So if we got a perfectly charged system, we're at 3,200 watts. But I'm going to continue this line up to our BTU line, and actually it's going to show about 26,000 BTUs. So in this particular example, if it had a 50-ounce charge, we've got a 26,000 BTU AC system that's consuming in power. The kilowatt demand is 3,200 watts, 3.2 kilowatts, okay? So we're okay with that, right? Now I'm going to ask one of you to tell me how much we want to undercharge the system. And I want you to tell me whether you want the 5%, 10%, or 15% undercharge. So, Herb, we're going to let you do this one. How much undercharge would you like to do this one at?
5%.
5%, good. I'm glad you said 10%, Herb, because 10% is easier to do the math on this. Okay? So I'm glad I gave you the chance, right? Because sometimes the attendee in class does say 10% and everything goes along very nice. Okay, but you're able to see this a lot easier. So watch this. Hey, 10% undercharge. It's only got 45 ounces in there. And didn't I tell you before that the charge is critical, plus or minus 2 ounces? Let's see what happens with 5 ounces undercharge. So we'll come up here to the kilowatt line. Watch this. Here we go. All the way across. Look at that. 2.6 kilowatts, 2,600 watts, huh? You're going to love this one. Watch. That's why I'm so glad that you did the 10%, Herb. Here we go. And if I bring this over here, look at that. It's not 22, it's not 26. What shall we call it?
24.
Yeah, maybe about 24,500 BTUs. That be okay? So look at that. We undercharged it by 10%. And look at how much cooling capacity we lost. Hardly anything. But look at the savings we have in electricity. And I got to tell you, that's what contractors are doing today. I'm going to shut this off here a second. Let's talk about this. Contractors are absolutely doing this today. They are mismatching systems on purpose. They might be purchasing a 3-ton system and putting a 4-ton coil in it, just so they could end up having higher superheat, or they're putting in a match system and they're undercharging them a little bit. So there's a couple of different ways that the contractors are dealing with this, and they're saying, well, if I just don't put in as much refrigerant as it's supposed to have, I can just lose a little bit, so maybe I can oversize the system even and undercharge it a little bit, and then I can save a whole lot on my electric bill. So the point is this, I told you that the systems are critical plus or minus 2 ounces. And we just said 10% is 5 ounces undercharge, but look at the electricity he's saving. Is this okay?
What happens when the load gets up?
The point is it okay to use? Is it okay to do? No! This is how we lose compressors. Gentlemen, ladies and gentlemen, what cools a compressor? From our days back in school, it's the temperature of the suction gas. And when we undercharge it over that, beyond that 2%, or that 2 ounces, when we undercharge it beyond the 2 ounces, the temperature of the suction gas goes up and it will overheat. Okay? So it's not good. You may run for a while, but you will eventually lose a compressor. You may save electricity for a while, but you lose a compressor. Typically, in all the classes that I teach on air conditioning, we do talk about this a lot, and we teach about compressor diagnostics. You know, just so you know, this is my background. I was a compressor man for many years. I got a lot of compressors, way too many to even talk about. So when I talk about this stuff, I know what I'm talking about, because when you replace a compressor, you better darn well know what caused that compressor to fail, because if you don't solve it, the next compressor fails, and then the next one does, okay? So again, this is why we're up here, to be able to show you this. But if we lost a little bit of AC here, a little bit of capacity, and we saved substantially in our power bill, watch what happens when we do the same thing with an overcharge, such as the beer can cold and the amperage and the 30 over ambient and all the rest of that stuff. 10%, gentlemen, 110% of the charge. Here we go. Let's run up here. Let's run up here. Let's run up here to the BTU line. Do you notice that's the BTU line? Look at this. Now we come all the way over here. Now we got an 18,000 BTU AC. Now look at the capacity that we lost by being 10% overcharged. And now let's continue. Let's continue all the way up here to the kilowatt line. And now take a look, maybe 4,100 watts, huh? Do you see what happens with an overcharge? We lose capacity and it costs us a fortune. Let's talk about it. The customer says, darn you and darn your air conditioner. You told me that if I purchased this new high efficiency system, it would cool the same way and my electric bill would be so much less. Well, I got to tell you, it runs forever, it never shuts off, doesn't cool the house, and my electric bill is sky high. And ladies and gentlemen, isn't that what we just did over here? Less capacity costs you a fortune in electric, runs constantly, and it cannot do the job. And guess what we do? We blow compressors. Okay? So again, capacity, electricity, undercharge, overcharge. So how about if we show you how to diagnose this stuff quickly and how to resolve the problem quickly? Okay? That's why we're here today. Are we okay with this so far? Okay, it's a simple chart, but it works. All right. Get rid of this. Now we come back, and because we did that, now we're going to go through one of the very first pages. And we're going to start out with the basics. We're going to show you a normal charge, undercharge, overcharge, and a restriction. Ooh, how about that? You understand this stuff: compressor, condenser, liquid line, evaporator. We're going to go clockwise. It don't make any difference which way we go, clockwise or counterclockwise, but that's a compressor. And with the compressor, we are pumping heat-laden vapor into the condenser. And by the way, we're going to talk about a 95-degree ambient temperature outside. How's that? And this central air conditioner, and we can call it a 3-ton, it's doing so good that the inside of the house is 75 degrees, nice and cool and dry. It's working great. So this is a normal system, and again, if it called for 50 ounces, that's exactly what we're putting into it. But under normal conditions, we would then have a fan that's blowing 95-degree air through a very hot condenser. And the compressor is discharging that heat-laden vapor. It discharges into the discharge line, that's your discharge line, into the top of the condenser. And of course, the top of the condenser with the vapor is much hotter than the 95-degree cool air. So the vapor gives up the BTUs to the very cool 95 degrees and condenses into a liquid. That's the change of state temperature. Well, then at the bottom of the condenser we have liquid. So we have liquid in that portion of the condenser. We have liquid in the liquid line of the condenser. And then we have liquid in the dryer, which is mounted right before. Now this is a picture of a capillary tube, but it could be a TXV or a restrictor orifice. And of course, if it's a capillary tube, we have liquid all the way through. But take a look at this, and we're going to stop here and talk about this for a minute. We have liquid in the bottom of the condenser, and the liquid goes all the way through until we reach the dryer, which is installed. And let's talk about this. The liquid dryer is installed in the place where it's most difficult to install, but it's the proper place. Inside the home, right before the metering device. It's a filter, it's a dryer. It's supposed to keep contaminants out of your metering device. The dryer is very easy to install outdoors, baking in the sun. A high-side dryer is designed to absorb moisture. We don't let it bake in the sun. We always want to shade a dryer. So the correct method, the recommended method, is to install a dryer inside the house, pointing down, so we don't have an oil trap. Okay, so that's why we show the drawing in this fashion. Okay, and again, it's more difficult to braze the. Let's go back. I'm going to finish talking. I forgot something. It's more difficult to braze the dryer inside the house than it is outside. And keep in mind, I just used the term braze. When you call for technical assistance, many times we will ask you, did you soft solder the unit in by using 95.5, or did you use high temperature brazing? The only acceptable method of installation is high temperature brazing. Silver brazing with Sulfos, or high percentage silver with silver solder. No 95.5. Low temperature soldering is for plumbing, low pressure. Brazing is what we use in refrigeration. So let's go back now. We have a normal system. And we actually, under these conditions, now have an evaporator that is completely full of liquid refrigerant, changing state, boiling, and it's absorbing BTUs. We actually, under these conditions, could say, as an example, that we have a return, let's say 80 degrees return. And let's just say everything is working fine, so the air goes through the coil, and we have a supply of 60 degrees. So we would have a 20-degree drop across the coil. And that would be terrific to have that. Now, at the end of the evaporator, of course, everything is working ideally. We now have vapor refrigerant going down the suction line and into the dome of the compressor, because the compressors are low-side domes. Again, a perfectly operating system. But let's talk a little bit more about this. For example, we're going to say that this is, in fact, a perfectly charged system, and only for the example, we're going to say that it is a 30 over ambient condenser. So if it's a 30 over ambient condenser, and if we know that the outdoor temperature is 95 degrees, this condenser would be what temperature then if it's 30 over? 125 degrees. But what we have to understand is that it is 125 degrees. In one place only, right there where it's changing state, that is the saturation temperature. If we have 125 degrees, it's where it's changing state, which means above it it's hotter, below it it's cooler. In fact, it's so hot that this is 125 degrees. Let's talk about that. How hot is it above the top of the condenser? The compressor is discharging into the top of the condenser. We said that we got a change of state at 125 degrees somewhere inside that condenser. So how hot is it? I don't know, maybe 160, 170 degrees. How hot is 160 and 170? Go home tonight and turn on the tub faucet, hot water alone, 100%. Stick your hand under there. And if you go, man, that's pretty hot. That's about 130 degrees. But leave it on and take your hand and go, wow! I'm telling you, that's like 140 degrees. So the discharge line, what I'm trying to impress upon you is that the discharge line coming out of a system, if you grab that line, your skin's going to stay there. 160, 170, 180 degrees. Gets very hot. But we don't care about that temperature. What we're concerned about is, let's go back to the overhead. We're concerned about the saturation temperature. This is the temperature, again, where the refrigerant is changing state. Remember, we have the gas giving up BTUs to the cool air, and so it condenses into liquid. We said that it's 125 degrees. How do we know it's 125 degrees? Just because I said that? We don't know that, except we have a method for us to be able to tell in seconds what temperature that is. Remember that every unit has got a service valve, a high-side service valve at the bottom of the condenser, and a low-side service valve just before the compressor on the suction line. So we have a high-side pressure, or a high-side service valve. Well, if we have a high-side service valve, ladies and gentlemen, we can take and put a pressure gauge on there. Now, this is R22 that we're talking about here. So R22, now you don't have to keep flipping your pages back and forth, but in your handout, on one of the pages, we actually have a PT chart. And if we look at 125 degrees, this is R22, temperature on the left side, and the pressure on the right side. By the way, we also have the pressures for R410A, and we'll talk about that later. But if we have 125 degrees, that means my pressure would be 278. So what I'm going to do here is, I'm going to say that we put our pressure gauge on here, and I read 278 psi. That's how I know that my temperature of my condenser is 125 degrees. I convert. I take my pressure from my gauge, and I have 278 psi, and I use a PT chart or read the gauge, and it says, hey, 278 is 125 degrees. Saturation temperature, condensing temperature, change of state temperature. It all means the same thing. That's the saturated line. It's condensing. Okay? So we know that that's 125 degrees. Now, let's go over to the low side. We said that we had 80 degree return and a 60 degree supply, and it's working terrific. That's about a 20 degree difference. Do you happen to know typically about what temperature that evaporator would be in order to get a 20 degree differential? Now you may know and you may not. It's actually about 40 degrees, correct, right. So Ray was just going to say that, but I beat him to that because I wanted him to have the right answer. But if that means we're saying that we have a 40 degree evaporator. That means the entire evaporator is full of liquid refrigerant, changing state, and we got 40 degrees. How do we know? Just because we said so? Just because I said so and Ray was going to back me up? That doesn't mean it's true. Well, ladies and gentlemen, it's the same way. We're going to take a pressure gauge, we're going to put it on our low side, because that's going to then measure our low side pressure. And under these conditions, we're going to be measuring about 68 psi. And if we look at a PT chart, let's go back and use it. So if I look at the PT chart and I come down on my pressure, 68 psi is about 40 degrees. So I hope you understand that all we need to do is put our pressure gauge on there to know the temperature of the evaporator. Is this clear? We put the pressure gauge on the high side to know what the change of state temperature is, although we know it's vapor on top and liquid at the bottom. And we put our pressure gauge on the low side to know what our evaporator temperature is, and the whole thing is full of liquid. Boiling, changing state. Picking up BTUs from the return air, and of course the supply then comes out cooler. And all that's left now is vapor. Okay? So now we know how to get the temperatures. Now, let's continue. Now let's take a thermometer, and let's stop here, and Jeff, we're going to show them the electronic thermometer again, because this is where you use this kind of an instrument in refrigeration. We're going to tell you to take a thermocouple. Now keep in mind, this is only one method of taking temperatures. Boy, I guess today they got all kinds of instruments. They've got little clamp-on accessories for digital thermometers that you can just clamp on these lines, and they are really terrific. I guess they even, some technicians even use the infrared, but I understand you got to go very close with it. Whatever method you have, as long as it's accurate, got to be accurate. But we're going to tell you that you can take a thermocouple and put it on your suction line and tape it. Take a piece of tape and tape it, and then take a piece of insulation, cloth, paper, anything. Insulate it and tape that so it doesn't come off. If we're going to be measuring suction line temperature, the sun is beating on it, we do not want to influence this by the sun. So on the suction line, tape it, insulate it, all right? Then at the same token, you can take another one or the same one and take a couple of readings and put this on the bottom of the condenser, on the liquid line, okay? You can put both of these, ladies and gentlemen, right close to your service valves, because the high side service valve is on the bottom of the condenser. We'll go back here to the transparency. The high side valve is close, the liquid line, where we want you to put the thermometer, is right by the high side valve, and the suction line temperature with the thermometer is right by the low side service valve. So the service valve is on the bottom of the condenser for the high side, and right before the compressor on the low side. Okay? Now, if we put a thermometer here, we know that this is all liquid, so I'm going to put a thermometer on the liquid line close to the service valve, and I'm going to, under these conditions, measure the liquid line temperature. And let's just say, as an example, I come up with 110 degrees. Now, let's make something very clear. I've got refrigerant, liquid refrigerant sitting in this condenser. The condenser is giving up the BTUs to the very cool 95 degrees. Isn't 125 hotter than 95? Isn't 110 hotter than 95? So not only does the hot vapor give it up, not only does the change of state temperature give it up, but the liquid in the bottom of the condenser also gives up BTUs to the cool 95 degrees. Well, how many degrees difference is the bottom of the condenser as compared to the saturation temperature of the condenser? How many degrees cooler is it?
15.
15. Gentlemen, that means we have 15 degrees of subcooling. And boy, do you have to know this to diagnose. But you see how easy it is to take. We're telling you, you can diagnose in 15 minutes. Let it run for a few minutes and take your subcooling. Measure your pressure. That's easy. Convert it. Stick a thermometer under. Let it run for a few minutes. Take a temperature reading. Subtract. Now you know your subcooling. Let me make something clear. If you can read subcooling, I got to tell you, subcooling is more important than superheat. And in all the classes they say, oh, you got to know superheat. That's fine. Yes, you do. But boy, is subcooling a clue to diagnosing. Okay? So I hope I'm making this clear enough that you understand subcooling. Now let's go do superheat. Now I can take, I know that my evaporator is 40 degrees. I can put a thermometer on my suction line. And holy cow, I measure 50 degrees. Isn't my suction line always warmer than my evaporator? It's got to be. Because the suction line runs from the evaporator. Let's talk. The suction line runs from the evaporator to the condenser. But to get from the evaporator to the condenser, maybe it's got to go through an attic, through a basement, outside. Could be 40 feet long, could be 150 feet long. But as it goes along, it's picking up BTUs. Why do you think we insulate them? We insulate them, yes, sure, to prevent sweating, but we insulate them to prevent the suction line from gaining too many BTUs. Because today we also charge by superheat, and we diagnose by superheat. All we know is that the suction line is warmer than the evaporator. In a technical class, we'll say, gee, what's the definition of superheat? Who cares? As long as we know that the suction line is warmer than the evaporator. That's what superheat means. As long as the technician knows what the superheat means on a system, he can diagnose. What is the definition of superheat again? I got to try to remember that one. Definition of superheat is something like it's warmer than the change of state temperature. That would be a method. Huh? Definition of subcooling, it would be below the temperature of the condensation temperature, which is still the saturated temperature. So again, there's different ways of talking about definitions. But definitions mean nothing if you don't know what they mean. So you understand, gentlemen, under these conditions, this suction line is how many degrees warmer than my evaporator?
10.
So I have 10 degrees of superheat. Let's make it clear. Superheat, suction line warmer than the evaporator. Subcooling, liquid line cooler than the change of state temperature in the condenser. See, we don't want to say it's cooler than the condenser. We want to say that it's cooler than the saturated temperature of the condenser. How's that? That's subcooling. Okay? All right. That's normal. If that's normal, let's do undercharge. Now we'll do an undercharge. And let's just say that all of the same things happened. Bink, 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 bink. Bink, bink. That means now I got more vapor, only a little bit of liquid now at the bottom. But I still got liquid. Still got liquid. And I still got liquid. And now I only have a little bit of liquid in the evaporator. And ping, 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 lots of superheat now. Okay? I got more vapor to pick up BTUs. Under these conditions, let's just say, I'm going to look at my PT chart so I can do this the right way. Yeah, let's do it this way. Let's say I take a pressure reading, and I'm going to look at 226 psi. See, that's different than 278, isn't it? I still got a 95 degree temperature outside, but I only got 226 psi. That means that my saturation temperature is 110 degrees. Right there. That's all. Right there. Okay?
How did you get that?
Lower pressure, lower temperature. If I am under, I'm only giving you this as an example. There's all kinds of ways to give you an example. What I did was, I said I want to bring my pressure down. So I came down to 200 and, where is it at? Right here, 226 psi. That gives me a saturation temperature of 110 degrees. Remember, if I know my pressure, I know what my saturation temperature is. So what I'm saying, Herb, is that we undercharge it. It's undercharged for whatever reason. Technician, leak, or something. Right now it's undercharged. I put my high side pressure gauge on, I read 226. I know that my saturation temperature is right there, 110 degrees. Isn't it true that I got more vapor and less liquid now? Over here was normal. Now I got more vapor, less liquid. Now I put a thermometer on. You're going to love this. And I have 107 degrees. I still got a 95-degree fan blowing air through it. Isn't 107 degrees still hotter than 95? How many degrees of subcooling have I got?
12.
107 from 110.
3.
3. I got 3 degrees of subcooling. Okay? Let's stop and talk again. Normal is 12 to 15 degrees of subcooling. See? Normal is 12 to 15. So right away you say 3. Well, holy cow, there's not enough refrigerant in there. That's your biggest clue. Okay? Now, if my subcooling went down because of an undercharge, watch what happens with the evaporator. I'm going to come over here now and I'll say that I now have a pressure reading of, I think it's 61 psi. Let me take a look at my pressure chart. If I have a 61, 35 degrees, do you see that? 61 psi is 35 degrees on my saturation temperature. So watch this now. I now have a 35 degree evaporator. Guess where it's 35? Only where the liquid is. See, now the house is getting hot. I no longer have an 80 degree return. The house is hot. Man, I got a 90 degree return. I can't even cool the house. If this pressure goes any lower, I'm going to end up with an ice ball once I get down below 32 degrees. All we're saying is that I put my pressure gauge on here. I got 61 psi. I ain't got 68 anymore. I got 61, I got a 35 degree evaporator. However, I come over here now and I put my thermometer on here and I have a 65 degree suction line. How many degrees warmer is my suction line than my evaporator?
30.
I have a 30 degrees of superheat. We know that the superheat changes, but I certainly don't want 30. When we start looking at a superheat charge, we know that I better have about 5 degrees, according to a superheat chart. But look, but you see what's happened here, and I guess I can put the camera on me, and I'll be talking about that back there. That's okay. You can put it back on me. Thank you. When it's undercharged, the subcooling goes down, and the superheat goes up. You know what normal is. Do we agree that the subcooling went down, superheat goes up? You have to understand that. Okay, we can go back here now. All right, if that's true now, this is crash course. This is why it's on video. You can go back and play it over and over. All right. All right, here we go. Let's do an overcharge. Is the pressure going to go up or down with an overcharge? Goes up. Oh, let's say I... Boom, 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 boom. Boom, 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 boom. Lots of liquid now. See it? Lots of liquid. Very little vapor. Sure is lots. Liquid. 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 Let's watch this. See? And very little vapor left. Lots of liquid, even in the suction line. Now, let's talk, if the pressure goes up, I'm going to try and use the example of 337 psi. Now if I come to my chart, 337 is 140 degrees. How's that? So I now have 140 degrees right there. Okay? And I put my thermometer on the liquid line, and I now have, let's just say, 110 degrees. Just so we can see what happens. Because now I have more liquid giving up the BTUs. Okay? How many degrees of subcooling have I got?
30.
140 degrees saturation.
30.
30, correct. I have 30 degrees. Normal is 12 to 15. When I'm overcharged, it's called stacking refrigerant. That is a term we use. Stacking refrigerant. Oh, we're stacking refrigerant. My subcooling is too high. Watch now. Now I put a pressure gauge here. Watch this. Is my pressure going to go up or down if I'm overcharged?
Go up.
Up. 85 psi. And if I look at my PT chart, 85 psi is about, it's actually about 51. We're going to use 50. Well, holy cow, I have a 50-degree evaporator now. Yeah, my pressure went up. 85 psi, gentlemen. My pressure went up. I have a 50-degree evaporator. And the technician says, the old-timers told me that if it isn't cold enough, grab the suction line and just keep adding more gas until it gets beer can cold. And I keep adding gas and they get colder. It's getting warmer. That's what happens. Okay, makes sense? How can it get colder when I'm raising my pressure? And let's go back here to the chart. How can it get warmer when the suction line is full of liquid? Pressure goes up, temperature goes up. But now, I already got a little bit of BTUs over here being absorbed by that vapor. So I'm going to put my thermometer on it. And I have 52 degrees. Suction line. How many degrees of superheat?
2.
2. 50-degree evaporator, 52-degree suction line. I got 2 degrees of superheat. Ready? We're getting to the good stuff here.
What is normal and super again?
What is normal what?
Superheat.
Superheat's all over the board, depending on conditions. That changes. But all we're trying to do is giving you an example of a 95-degree day, normal. Let's go back, and then I'll go back again. But overcharge, subcooling goes up, and superheat goes down. Let's go back. You've got to know this. And I've got a chart that you can refer to that'll make it so easy. Just trying to get you to understand this. And the way you understand this is by practicing with it a little bit. I tell students when I teach this to them, if they understand it today, that means tonight they have to go home and teach it to a member of their family, really. And if they're married, I tell them to teach it to their spouse, or if they got kids, sit down and teach it to their kids, and it should take them at least an hour to do that. And it works. That's the only way that you can remember this. Normal. But if it's undercharged, subcooling goes down. Superheat goes up. Overcharged, subcooling goes up. Superheat goes down. Got that? We okay?
Yes.
Now we get into diagnosis. I didn't say this stuff was easy.
Now the restriction.
That's right. Now let's restrict it. Let's say the contractor wanted to save $7 on a $3,000 job and he doesn't put a dryer in here. Let's just say that. And so he's got a piece of something that gets plugged in the orifice. Now let's stop here. If you can diagnose a complete 100% restriction, you'll be able to diagnose a partial restriction because it's just not as bad. So 100% restriction, no flow. Maybe the contractor used 95.5 and he got balls of solder that got stuck in the orifice. And believe me, I got plenty of those envelopes in my desk where the contractor said, I'll send you the balls of solder. After I have them pull it apart on the job, they say, oh yeah, I got 3 little balls in there. I say, why are you using soft solder? Or they just don't put it in there as garbage that floats through. The point is, if you can understand a 100% restriction, you can understand a partially restricted system. We're going to talk about perfectly charged. Let's say it calls for 50 ounces, and let's say it's got 50 ounces in there. Okay? All right, so here we go. So now, and I'm going to ask you a question, and I want you to give me, because Kevin, you've been through this, and Herb, you may have, but I want you to give me the question that the technicians will always respond to. Okay? So we say, vapor, 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 vapor. Let's go backwards a little bit. We suck everything out of here. Boom, 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 boom. Now we got a vacuum. Agreed? Now we know we can't run a compressor like that, but just for purposes of understanding this, we got nothing else to bring out. So under those conditions, we got vapor, 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 and whew, lots of liquid. Wow, it looks like that, doesn't it? We're stacking refrigerant because we have a 100% restriction. So we come down to here, and we come down to here, and that's as far as it goes. That's it. Now, let's go over here and put our pressure gauge on the high side, and put our pressure gauge on the low side, and of course the low side shows a vacuum with a 100% restriction. And we have the pressure gauge on the high side. Let's talk about it. 100% restriction, perfectly charged, and the technician puts the gauge on the high side. Now keep in mind, high side gauges, if you peg the needle, there's safeties in most gauges and you don't really hurt it, but you got to be careful with, you have to be careful with high side gauges. My question to you is, under these conditions, will that pressure go up or down, first of all, but if it goes up, how high is it going to go up?
Go up, pressure kicks compressor on.
I mean, look at, remember, 100% restriction, no flow. Everything is out of the evaporator. Push it all into the condenser. Stack, 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 stack. And my question to you is, man, how high will it go? Right? Right? If you understand this, you can understand partial. You know how high it's going to go? I gotta go find it. I gotta go find it.
381.
Ooh. Here it goes. 100% restriction. Here. I forgot it already. Wait a minute. It goes to. Ooh. Here's the third number.
381.
Here's the second number.
381.
Ah!
181. Really? 181.
That's it.
180.
What does that equal?
95.
That equals 95 degrees.
Yeah.
Isn't that the outside temperature? Because that's all you're going to read is 181. Sorry, I get excited. I get so excited about this stuff. This is so good because once you learn this, you can do anything in refrigeration. Gentlemen, this is like a tank of gas sitting on a table. When you get this system delivered, it is completely charged with a charge enough for a 25 foot of standard line set. All I'm saying to you is we said that it's 100% restricted, and the technician puts his gauge on here and he says, oh, it's low. But gentlemen, the condenser is big enough to hold the entire charge and then some. So where's it going to go? I didn't back the refrigerant up to the compressor. We didn't add any gas. All I said to you was perfectly charged. Where does the pressure go? Nowhere. It's a tank of gas. If you put this tank of gas outside in 95-degree air, in the shade, not in the sun, always at the shade, that's 95-degree shade, and you put a pressure gauge on it, 95 degrees R22 will read 181 psi. Because the PT chart says 181, 95 degrees. But the technician said, now remember, do we agree, as compared to normal pressures, do we agree that a vacuum is lower on the low side? And that the 181 is lower on the high side also, so they're both low? So if the technician says, oh, I have a low side, and I have a low high side, I must be undercharged. Because didn't an undercharge give you a low high side and a low side? He says, oh, I don't have enough gas. Now the technician says, I'll make it cooler. Let's add gas. Now the pressure goes up. See what I mean? Gentlemen, do you understand that a partial restriction is going to give you a lower pressure high side and a lower pressure low side, but you have only one clue that tells you it's partially restricted. Right there. Subcooling. Because when you are partially restricted, your subcooling goes down. I got to remember stuff myself. The subcooling goes down and the superheat goes up. Watch. Let's do it this way. Subcooling goes down and superheat goes up. When we did an overcharge, the subcooling went down. What am I talking about? You're confusing me. I'm believing you. Reversed. Sorry. This is why live classes are so much easier than video. But these things happen, and they happen in the field. Subcooling goes up. Because when we did it on the high side for overcharge, it went up, correct? And the superheat went down. So superheat goes down, subcooling went up. Let's go back. On an undercharge, my superheat went up and the subcooling went down. See, gentlemen, or ladies and gentlemen, it's the terminology that throws you. It's all confused. You say up and down and superheat. It's all confusing. But watch now. Let's go back and review. Undercharge. Subcooling is down. Superheat is up. On an overcharge, subcooling is up. Superheat is down. On a restriction, subcooling is up and superheat is up. That's what's different. And you say, holy cow, look at this. And I drew all these pictures on my notes, and I drew all of this, and then I come over here and I say, I'm so confused. But now I make your life easy, because that's what we're here for, okay? I only did this as the basics, so you can understand this. And you can see I teach this all the time. You got to be real sure about what you're talking about, okay? Subcooling and superheat are important. We just said, I'm going to review one more time and then show you the chart. Undercharge, subcooling down, superheat up. Overcharge, subcooling up, superheat down. Restriction, subcooling up because we're stacking refrigerant. Superheat up because we're starving the evaporator. Over here on an undercharge, we starve the evaporator. On a restriction, we're starving the evaporator. So the clue to a restriction is up, up. So watch. Now go to your handout and find that page. And you're going to love it. It's on page 4. Here's the answer. And so you say discharge pressure, which is the high side pressure. We're only going to do the first 3. Suction pressure, superheat, and subcooling. That's all we need to do. So if it's overcharged, discharge pressure is high, suction pressure is high. Do we agree with that? Here it is. Overcharge, superheat low, subcooling high. Let's go look. Superheat low, subcooling high with an overcharge. Come on back over here. Overcharged. Superheat low, subcooling high. Same thing. Go to the next one. Undercharged. Low, low, of course, pressures. Superheat high, subcooling low. Let's go see. Undercharged. Superheat high, subcooling low. But look at the restriction. Restriction. Pressures, low, low. Sure, it looks like an undercharge. Is it low, low right above it? If it's undercharged, low, 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 low. But look at your superheat subcooling, high, high. That's your clue. So, ladies and gentlemen, and the technicians in the field, go ahead and write yourself some notes like this. It's a very busy transparency copy right now. A lot of stuff in here. But these are the things that you want to teach to somebody. When you teach it 20 times, you get better at it. That's all I can tell you, really. But the chart helps. You don't have to be perfect with it. All you got to do is remember this, and you got to remember that subcooling typically is 12 to 15 degrees for normal. Is this a good chart?
Yes.
Okay? I think this helps. This is tough, and I have to tell you, ladies and gentlemen, in a semester, we have to review with students superheat and subcooling at least a half a dozen times. Because no matter what you think you know today, you'll forget it tomorrow. And that's why you have to teach it to somebody. Okay? Are we all right with that? Okay. That's enough on that topic? Beat that one up, right? Okay. Whew. All right, here we go. We're getting there. Now, you have on the next page a chart. And that would be your page 5. Ladies and gentlemen, this is a generic chart. We always want you to charge the systems according to manufacturer's instructions. Follow their guidelines. We're about to give you some here real quick. When I say generic superheat chart, is because the chart after this one is a little bit more complicated. But if you got a mismatch, new condenser, existing evaporator, you only need to know 2 things. The ambient temperature, check the outdoor temperature in the shade, put your thermometer in the shade, and check the outdoor temperature, and stick your thermometer in the return, and you got to know what the return is. That's all. This is a one-fits-all chart. This is the only one that I'm going to go through with you here. It says right on top, it's charging by superheat for cap tubes or orifice when the charge is not known. And so if there's any reason why you don't know what the exact charge is, or you got a mismatch and the contractor put in a different size coil, you charge it according to this and that system will work. The one down here is for TXVs. In this area we don't use a lot of TXVs, but if you're in an area that does, you can do the same thing, and you would charge your mismatched systems by knowing by the subcooling. And again, under normal conditions, you want 12 to 15 degrees of subcooling. But I want to jump back here to superheat, and I'll let you do a couple of these here. Let's talk about that chart. It's a generic chart, once fits all. I've been using this chart for many years. Is it perfect? No, but you will be within your plus or minus 2 ounces. And if you charge it according to this chart, you will not blow a compressor. So that's pretty good, isn't it? All right, here you go. Let's give an example. Ray, give me any temperature you want, and we're going to work with it.
85 degrees. 85
degrees. So we're saying it's 85 degrees outside. Herb, you're going to check the return air temperature, and you see that you can go anywhere from 65 to 85. So whatever the return air temperature is, you give me one.
75.
75 degree return air temperature. So you see the superheat that you're looking for? 10. It's that easy. So if your superheat, now here's the question. If your superheat's too high, do we add or recover? See, now you got to go back and say, oh man, I got to look at the chart. And it's too high, that's right. All right, and again, because only for purposes of conserving time and we're doing a video, remember, if the superheat is 20 and you want 10, well, you need to lower it. And you lower it by adding gas, okay? But if the superheat is too low, you got too much gas in there, and maybe you only got 5 degrees, then you want to recover. We don't vent anymore, we recover refrigerant, okay? All right, that's one example. Jeff, give me a nice hot day.
95.
95, so we're going to do 95. Kevin, it's kind of working. Give me a return air temperature.
80.
Wait a minute, my pen's leaking again? Okay, got it. Okay, 80 degrees. There you are, 95. I'm sorry, 95 outside, 80 degree return, you want 5 degrees of superheat. Well, you say, well, hey, what's the matter with that chart? Look at this.
Yeah.
Look at all the fives. 5, 5, 5. Yeah. When it's hot outside, we want low superheat. When it's cool outside, we want high superheat. How come? Let's talk. My hands are all full of the pen stuff, but that's okay. It's only a video. Why do we want low superheat on a hot day and high superheat on a cool day? Remember what superheat is. It's the amount of refrigerant, the temperature of the suction gas coming back to the compressor. We're talking about a fixed orifice. It's a fixed restriction. On a hot day, ladies and gentlemen, where does our high side pressure go? Does it go up or down? On a hot day, it goes up. Okay? So on a cool day, pressure goes down. All right, so let's take an example. Let's take a garden hose. That would be like a capillary tube, right? It's a fixed restriction. Take the garden hose and hook it up to the house. That's about 40 pounds water pressure, right? Take it and turn on the spigot and just sit there. And of course the water goes like that, right? You got a lot of water coming out, 40 psi. But now let's compare that to a hot day on a condenser where the pressure goes up. Take the garden hose off and call over the fire truck and stick it on there. Now maybe you got 120 pounds pressure now, right? Same restriction, higher pressure. Now sit there with the spigot open and it goes across the street. More water, more liquid. Okay? So it's the same thing with a fixed restriction. The higher the pressure behind it, the more refrigerant it pushes into that evaporator, more refrigerant is apt to go down that suction line. Which is why we never want zero superheat. Because zero superheat means the suction line is the same temperature as the evaporator. And that means it's all liquid. We don't want any liquid to come back to the compressor. Okay? But now you understand that if in fact we have a cool day, we want some high superheats. And so gentlemen, ladies and gentlemen, you can charge a system down to 60-degree outdoor temperature. But wait a minute. What happens if we get up to 105 degrees or 107 degrees outside temperature? Now what do we do? Nothing. You cannot complete the charge. That's the real world. You have to come back when it's on the chart if you want to do a proper charge. This is why in the Chicagoland area, I think our design temperature is 95, 97 degrees, but in some of the other southern states, and now we have a southern Indiana district, that's where they even use heat pumps, and they do have a higher system, or a higher design temperature. So their systems, if they have restrictor orifices, you could blow a compressor. This is why in Phoenix, where we have a very high design temperature, we cannot use that chart. In Phoenix, you could get up to 115, 118 degrees. If you use a restrictor, you'll have a zero superheat probably at 108 degrees or something. So they have to use all TXVs in very hot climates. No restrictors. In our area, it's mostly restrictors because it's less expensive. In some of these southern states, it's TXVs. And now we understand why, though. Okay? So, I don't want to spend a lot of time on this, but you understand. Let's give it one more shot. Herb, give me an outdoor temperature in between. Let's see if we can do it. Let's see how hard you're going to make this for us. I don't want a round number. I want an odd number there.
74.
Okay, so he says 74. So let's see. That's going to be right about here. And Ray, give me an odd number of a return air temperature in the house because it could be different.
Make it 76.
76. So let's see. So 76 is going to be right around here. So I'm going to come over here. So if it's over here, so you see, it's coming closer to the 25, and it's below the 17. So if it's below the 17, it's actually coming closer to the 20. Do you notice that? This one over here is coming closer to the 25, and this one over here is, you said 74, is coming closer to the 20. Aren't both of these higher than 17? But they're not quite there. What do you think you might want to shoot for with this one?
The average.
Yeah, so give me something.
23, 22 and a half.
No, I'm just wondering, see, because this one over here is going to counteract this one, would I be correct in beginning shooting for like 20 degrees? I think that's about what I'd be looking for right here. Because 75 and 75 would be 17, but we're a little bit above it here and we're a little bit below it here. Maybe a 19 degrees superheat, huh? What do you think? You guys in agreement or not?
Mm-hmm.
I'm just trying to interpolate here. I didn't say this was easy. But hold it. Let's do this. Let's say, hey, 75 and thermometers could be off a little bit, right? Yeah. So let's go right back to the 75 and the 75.
I think 21 would probably be a good one.
I think 19.
Close enough.
It's close enough.
Yeah.
The point is, when it gets hot, ladies and gentlemen, at 100 degrees, you do not want zero superheat. That's all we're trying to do. We don't want it to go down to zero when it gets very hot. So interpolate the best way you can, and it is a generic chart, okay? It's as close to being perfect as you can get. Are you okay? Because now I'm going to get you perfect. That's close to being perfect. But now I'm going to get you perfect. Okay, here we go. And this will be the last segment before we get into the job site, and then we're all done here pretty soon. So you now have a page 6, and it looks like that. So in your handouts, you got page 6, and this is the charging chart, excuse me, that is on the access panel of the Ring-Rude Weather King condensers. And when you look at this chart, you say, oh, that's easy, I just have to follow this and I can charge it. Because Phil said if I follow the chart, it works perfect. Problem is, you need a magnifying glass. I have taught classes from this chart. I can't do a class on this chart to be really perfect with it in less than 2 hours. The whole chart. So today we say, forget it. You don't need any of this stuff. But, just so you understand, this is a liquid pressure chart. This is a superheat chart. And then down here is ounces per foot chart. But if I bring you back up here to pressure chart, without having to spend a lot of time on this, the statements that are above here say that you can use this chart if you install an AC system with an orifice or a TXV. But the house has got to be hot to use it. See, this up here says if the house is hot, go ahead and use this chart. I don't even want to take the time to read those 2 sentences because you got to read it several times and explain it. So let me just explain it so we can conserve time. It says if your house is hot, use the pressure chart, and if it's a TXV, use the pressure chart again if the house is hot. So if it's 95 degrees and you're just putting in a system, how warm is the house? The windows are open, it's 95 degrees. So follow the pressure chart and you're close enough for a TXV and you go home and you're done. But again, if you got an orifice, that statement says start with the pressure chart and then come back tomorrow when the house is cool so you can finish it by the superheat chart that's on this chart. That's what that says. You have to bring it down within 2 degrees of the normal comfort system in order to finish the chart. So we can start with the pressure chart. I'm not going to spend time going through this. It's good to know this, and if you want to learn it, and I tell students if they want to learn how to do this, you got to sit at home yourself and read this. You read it word for word. It's great. But I don't think you can get through this in less than an hour and a half by yourself, just by reading it. Trying to understand the ambient temperatures and the pressures and the sizes, but it's great stuff. But again, the conditions have to be perfect for you to come down all the way down to here to use the superheat chart. It's another superheat chart. We're not going to spend time on it. Because again, ladies and gentlemen, that's the perfect world that's pretty close to get to being perfect. So forget it. Let's do the perfect world. That's very quick. We just told you that we're going to be teaching you here how to diagnose in 20 minutes. What you can do to eliminate some problems very quickly. Real world stuff. And what I teach you, you can count on it being accurate. Again, I'm a compressor guy. So what I teach you, and that's my background, what I teach you works. That's what I use, okay? All right, here we go. When we come down here, we're going to talk about the system total charge. So this is the only thing that we're going to be reading off of this chart. We're going to get you through this, we fill out a job site, and then we're done. It says installer. Determine the complete system total charge by using the proper item below. Stamp or mark this value on the rating plate in the system total charge block. Let's stop and talk about that. It's telling the installer, figure out the charge, and then once you figure it out, put it with a magic marker or something, a permanent marker, or some way, put it on the access panel so all technicians know that X amount of ounces are in the system. That's all they're saying there. Now, we go on. It says, outdoor unit charge. It says, add per foot value shown below for each foot over 25-foot liquid line to the factory charge. Subtract per foot value shown below for each foot under 25-foot liquid line from factory charge. Let's stop and talk. What they're telling you there is that all the condensers from Rheem manufacturing, Rheem Root Weather King, come completely charged and are set up to handle 25 feet of standard line set. So if it takes X amount of ounces, they add some more, and that'll handle the 25 foot of the line set. So whatever that data tag says, that already included in that charge is 25 feet of the liquid line. See, I don't want to say the first 25 feet because we could be over or under 25 feet. And that's what that statement says. It says if you're over, you better add, or if you're under, you better recover. Okay? All right. Now, so how much are we talking about? Well, we're only going to be talking about three sizes here. Quarter, 3/8, and 5/16. Do you see that a 1/4 inch liquid line is 0.3 ounces per foot? Do you see that a 3/8 liquid line is 0.6 ounces per foot? And the 5/16 is 0.4. Okay? All right. Now we're going to do a little bit of math. You watch me, because sometimes I make mistakes on this. If we have a 1/4 inch line, and we said that that is 0.3 ounces per foot, that means already included is 0.3 ounces times 25 feet, and that would equal what? Isn't that 7.5 ounces?
Yes.
So that's already in the data tag, or it's already included in the data tag charge, okay? Or if we have a 5/16, that is 0.4 times 25, and that would equal 10 ounces, okay? Or if you have a 3/8, that would be 0.6 times 25, and that would equal 15 ounces. We all agree on that.
Yes.
So the units that we have different line sets that are considered standard, and already included is that many ounces. Just for an example, because I want to be able to draw this up here so you can understand it. You know, it's one thing to be able to understand it, but it's another thing to be able to draw it so you can understand it. We're going to use an example of a data tag, and let's just say it's a 3-ton. We're going to use an example that says that the data tag that's sitting on there says that it contains R22 and it contains 51.7 ounces of refrigerant. Only as an example. Well, if that system has 51.7, we still don't know what the standard line set is, but if it was a 1/4 inch standard line set, it would already include 7.5 ounces. That would be included in there, see? But if it had 5/16, it would already have 10 ounces in there. And if it was 3/8, it would already have 15 ounces in there. Question is, what's the line set that we use for a liquid line when we install ACs? And really, you may know and you may not, but I'm going to tell you the answer that we always get from the technician. So if you think you know, I want you to say that, and I'll tell you whether that's the answer we get. So if I say to the group, what size liquid line do we use when we install a 3-ton AC? What's the diameter? Is it 1/4, 5/16, or 3/8? 3/8, right?
Yes.
Okay. So Kevin's nodding, and Herb, and Ray. We use 3/8. That's what technicians install. They install 3/8. And then I say, well, what do you install with a 1.5 tons? Well, 3/8, right? And what do you install with 4-ton? Well, 3/8. What do you install with 5-ton? 3/8. So we install 3/8 for everything. So some got to be wrong. And we say, why? That's what we carry. But you know what? That's good. That's good that you carry, because you only have to work with one size. So go ahead and work with one size, but compensate for it. That's all we're saying. Well, we say, well, how do we know which is which? Well, let's do this. Let me go get rid of all this stuff that I just put up here. Now, I'm trying to remember that figure that I used. We're going to use 51.7 as an example, okay? And I want you to turn to your page 7. There's another chart. Okay, here we go. And it says, we're only going to use the first 2 columns up here. That makes it easy. Because on the left side, we have the sizes of the AC from 1.5 tons to 5 tons. And take a look at the line size for liquid line. This is liquid line size chart. Do you notice that you have all different sizes? And do you notice that a lot of them have the asterisk, the star? So let's go down to 3 ton. What is the standard? Because the asterisk, if you come down here, says standard line size. What is the standard line size for a 3 ton?
5/16.
See, 5/16. Okay? That's the standard. And that's what is included. So if we have 51.7 ounces on a 3 ton, and we said that the 5/16 was 10 ounces for the first 25 feet, that 51.7 already includes 10 ounces. But you're not using 5/16, you're using 3/8. Now we got to compensate, okay? All right, so here we go. Look at this though, huh? The only time we start look at this, 3.5 ton is 5/16 too. 4 and 5 ton are 3/8. And now take a look at the 2.5 ton. Look at that. 2 sizes different, 1/4 inch. See? So, should we be installing 3 different sizes? Nah, it's too hard to keep carrying all the sizes. It's okay, all we got to do is add a little bit of refrigerant. That's all we're saying. That's only for the first 25 feet. Okay? And you can still use the same, and you got to follow the charts. And of course, you got lengths, and you got vertical separation, and the charts, that could take 1.5 hours just to go through this chart. But I just wanted you to see that part. So let's go and do something, but why are we doing this? 51.7. Why didn't I just say 50? Because I didn't want to. I wanted to use a decimal. Because that's what we're doing here today, gentlemen. We're going to show you how to take care of a problem. And if you have any problem at all determining what the correct refrigerant charge is, recover it and recharge it. What are you going to mess around with superheat for? Superheat is terrific. Superheat works to tweak a charge on a PM check where there's nothing wrong. That's what we use superheat today for. We didn't teach this 2 years ago about exact charge. We were teaching superheat 2 years ago because we didn't have accurate scales. Today we got scales that are in increments of 1/10 of an ounce. So 51.7 is a piece of cake. Let's talk about this a little bit. I'm going to grab the scale over here. And all we're saying to you is it's going to take you longer to figure out the refrigerant charge than it is to recover and recharge. It's going to take you longer to do the math because you're going to say, well, now I got to go measure that line set, and I have to crawl in a crawl space. I have to use my tape, and I have to go in the attic, and I have to measure that, and I have to measure that liquid line. It's going to take me 20 minutes to do that. That's right. How long do you think it's going to take you to recover and recharge? Oh, and technicians say, well, gee, I can't recover. Let's talk about that. How long is it going to take you to recover 50 ounces? How long does it take you to recover 90 ounces? And the technician says, oh man, it takes me 45 minutes. Oh, and of course another technician says, well, it takes me 1.5 hours. Why? We're going to show you how to do it in 5 minutes. How's that? Recover. Recover in 5 minutes. Is that okay? Yeah, that's really not right. We're going to show you how to recover in 4.5 minutes. How's that? That's even better. So if I can show you how to recover, and remember, what I tell you is good. I'm a compressor guy. I have to do this stuff right. So we're going to show you how to recover in less than 5 minutes. And if you have to figure out your charge, and let's say you have determined it to be 51.7 ounces, and you have a scale that's in increments of 1/10 of an ounce, how long does it take you to charge 51.7 ounces into a system? Minutes? So how about recover and recharge in less than 10 minutes? That's good now, isn't it? That could be part of your 20-minute diagnosis. Why are you messing around with charge? You say, gee, I don't know if the charge is correct. There's been 7 people out here before me. I don't know if I'm under. I don't know if I'm over, and my superheat's here, and I have to add a little bit here. Now I got to let it run, and I have to go and take my inside temperature, and then I have to go and take my pressure again. I have to look at my high side for subcooling. 45 minutes minimum. That's if the conditions are right. If the house is cool, the house has got to be cool. So forget it. We don't teach that anymore. It's great for tweaking a charge. Superheat is great for tweaking a charge. But if you don't know what the charge is, recover and recharge in less than 10 minutes. So how do we recover in less than 5? When a technician says, yeah, I put my recovery unit on, I start recovering, it goes down into the 10-inch vacuum, and then it shuts off, and then my gauges start to go up again. And then I turn it on again, then it goes down to a 10-minute evacuation, or into a 10-inch vacuum, and then it shuts off, and then the gauges go up again. Yeah, because the refrigerant is in the oil of the compressor. If the system was not running, let's say you even had a dead compressor for whatever reason, heat the compressor. That's the clue. In classes, I bring a commercial heat gun in here. They only cost like $65. The first thing to do when you know that you have to recover is you take your heat gun and you hook it up to 118.6 volts, right? Right. And you take it and you put it and you aim it towards the sump of the compressor, where the oil is, because that's where the refrigerant is migrating. If you don't heat it, the refrigerant migrates to that oil, the compressor gets sweaty, sometimes they even frost because all the refrigerant is in there boiling off. All you're doing is creating a low side pressure and it's sitting there boiling off, but it's migrating to the low pressure. So you heat the sump. While you're gathering all the rest of your tools from your truck, the heat gun is heating the sump of the compressor. If you don't have a heat gun, you got to sit there with a torch. Now that takes time because you got to sit there so you don't burn anything while you're flashing the compressor with the torch. You don't get the sump red hot with a torch. You can get it nice and hot with a heat gun, but you don't do that with a torch. But I'm saying that there are methods for a sealed system person to heat the sump of a compressor. But you don't want to waste time. Stick the heat gun on it. Go gather your tools. Come back. Now the top of that compressor is nice and warm. Start recovering. 4.5 minutes later, boom! It's all in a tank. I don't care how much you got there. It's quick. Now, once you recover it, you say, okay, now I got to go measure things and all this and figure out my line set. That's what we're going to do right now, is figure out what the exact charge is. Once you figure out the exact charge, you say, okay, let me go get my scale. So we now carry scales again. They used to be in half-ounce increments, you know. Today they're in 10-ounce increments. Do any of you have a quarter in your pocket? 25 cents. I'd be looking for 5 of them if you got them. We're going to show you how we demonstrate this in a class. Yeah, if you have 5, I'll make sure you get them all back. And I don't know if you can see this, Jeff, on the camera, but this is the scale. It's got a nice platform. Ladies and gentlemen, you can record everything on the scale, how much you recover, how much you add. But we take this and we turn it on, of course, and we zero it. Now, in order to demonstrate it, to show you how sensitive it is, and again, I don't know whether you can get this, Jeff, it's okay if you don't. I'm going to try and keep it as steady as I can, okay? If I throw a quarter on there anywhere, can you see what that registered?
0.2.
0.2.
Yep.
Should be 0.4, 0.6, 0.8, 1 ounce. Is it?
Mm-hmm.
Yeah, how about that, huh? Isn't that great? What a great way to demonstrate a scale. You talk about accurate. I'll keep your quarters up here until break. Let me tell you what this is all about, gentlemen. And I do talk about this in class. This scale will keep you out of prison. The EPA, and Jeff's even been doing some recent inquiries, you know, the law has been written for recovery since about 1993. It's very vague, hard to interpret. Even the EPA people don't know how to interpret it. What is required? That you be squeaky clean. We as a distributor must know everybody that we sell refrigerant to. We have to keep records, have to keep copies of CFC cards. The contractor must be squeaky clean. The EPA will walk in unannounced, ask for the records. That hasn't happened here in Chicago for 2 years, but it did 3 years ago. They come in unannounced, ask for the records. All you need to do is take all of your service calls with sealed system repairs, showing how much you recovered, how much you added, and just have that all in a binder, and then they'll want to know who you purchased your refrigerant from, and they'll also want to know what you did with your recovered refrigerant. They'll want to see that you brought your recovery tanks back to be reclaimed. Okay? So what they're looking for is records, and how much more perfect of a record can you give them to say that on this job I recovered 9.7 ounces. 9.7, huh? I'm sorry. 9, let's see, how can I do this? Oh shoot, how about 90.7 ounces, okay? So however that translate into pounds. So I recovered 90.7, that's 90 ounces and 7/10 of an ounce. 90 ounces plus 7/10. I did it in a decimal. How much more accurate can you be than a decimal? How many pounds is that, Kevin? You using any calculator?
5.668.
How many?
5.668.
5.668 pounds, right?
Yes.
Okay, but the point is, if you can show them that your records are accurate, how much are you recovering? See, how much are you putting into the system? That makes you accurate. So I was teasing a little bit, but really EPA isn't teasing. They're very serious about fines, and these are Class 2 felonies. So if you vent, if they want to, they can do those things to you, and they really scare the heck out of me. So I only talk to EPA people and lawyers in a technical manner, because that's all I know. I cannot talk their legal language. When lawyers call about customers and so forth, I talk to them technically. Okay. So again, you now know what the scale looks like. Now we're going to show you how to use it, and of course, at other classes we can demonstrate that. But if you put your recovery tank on there, all you do is zero it. You recover back into the tank, and then it shows you exactly how much you recovered. If you start to add gas and you say, I want to put in 51.7, you start adding the refrigerant by whatever method. The methods are put it to the high side, not running, or low side, running. Okay? And you just keep letting the refrigerant go in until you reach your 51.7 ounces. Okay? All right, so we okay with that so far? Now we have to figure out some line sets. Okay. So let's just say, now you're going to love this, and I promise to give you back a quarter. Okay.
He gave you $1.50, you know.
Huh?
Did you give him $1.50?
Yeah, right. Let's just say, as an example, we have a 3-ton system. And on the tag, it says R22, and it says 51.7 ounces. Now, as an example, I'm only giving you an example, let's just say we're putting in a 40-foot line, and we're doing it 3/8. So now we're one size above the standard liquid line size. Okay, so it should be 5/16, but we're going above to the 3/8. Now, for the first 25 foot, we have to figure out the difference, gentlemen. The ream only put in 10 ounces, but we really need 15. We can figure it that way too, but if I take the first 25 feet, the difference remember, 5/16, let's go down here and do this down here. A quarter was 0.3 per foot, and 5/16. Are you still able to see that on the bottom there, Jeff? You okay with that?
Yes.
Okay, 5/16 is 0.4, and 3/8 is 0.6. Are we okay with that? So the first 25 foot, the difference, because you're using a bigger line, is 3/8, and we know that the difference between 5/16 and 3/8 is 2/10. So I want to take 0.2 times the first 25 feet, and that would equal 5 ounces. Is that okay? Try and draw a line here so we don't get confused. Okay? So now I have to add already 5 ounces. Now, I also have 15 feet of extra 3/8 line because I'm putting in 40 feet. That's 15 feet beyond the 25 feet, correct? So now I have to take how much times 15? 0.6 times 15 is how much? Is that 9 ounces? 0.6 times 15 is 9 ounces, correct? But we ain't done yet. Let's talk. Because we're a good contractor. We're going to spend that $7 or $8 extra and put in a liquid line dryer before the metering device inside the house in the shade pointed down. And because it's a liquid line dryer, it holds refrigerant. We have to add refrigerant for that. So would you now please turn over to page 8, and are you going to love this? I'm going to keep my notes up here, but I have the other copy. This is a tech data sheet that I just got yesterday. It's an updated sheet, and it shows the 2 size dryers that we use, ladies and gentlemen. The first one here, the 8 cubic inch dryer, is from 1.5 tons to 3 tons. Now, if you run all the way down the line, do you see how much refrigerant we use for R22? See that? 8.1 ounces. Do you notice that a 3.5 to 5 ton, you would add 10.1 ounces?
Just for the... That's a lot, isn't it?
Yeah, but you, remember, the systems are critical, plus or minus 2 ounces. But you see why I said it's updated? Do you notice I also gave you the 410A refrigerant? So you even got the refrigerant charges for those, okay? All right. So the point is, right now, we know that it's a 3-ton system. We have to also add 8.1. So now we're going to put down dryer. And so let's put down 8.1. And that should be our total system charge. So if I add all that up, let's see, I should have 8. Is this right? I come up with 73.8, am I right? Is that okay?
Yeah.
Right.
So you see, my 51.7 has changed, hasn't it?
What'd you come up with?
I had to add for the extra 15 feet, I had to add for my dryer, and I had to put the difference in there for the standard line set. Do you understand why I said right now it takes you longer to do the math than it does to recover and recharge? But once you do that math and you get quick with it, recovering and recharging is the way to go. And let's talk about this a little bit. And at that point, ladies and gentlemen, you don't have to touch that charge at all. You can leave your gauges on it to diagnose if you want. But charge is out of the question. Now look for other things, like ductwork, dirty A-coil, dirty condenser, dirty secondary coil on a 90-plus furnace, huh? Dirty blower wheel. But you don't have to alter the charge. Isn't it neat? But you say, yeah, are we okay with this? Can I erase this one?
Mm-hmm.
You okay? And you say, yeah, but what about a short one? What about less than 25 feet? Well, I made an example of that too. Let's try this. 3-ton. And the tag says R2251.7. And 15-foot line set. And we go using 15 feet of 3/8. How's that? So we're 10 feet shorter, but we're using 3/8, which is bigger. So the first 15 feet, which is all we're working with, the difference should be 0.2 times 15. Let's see, that would equal what? Is that 3 ounces?
3 ounces, correct.
That's 3 ounces. And let's see, the difference, the 10 feet, I got to take away 10 feet. So I got less, that's what it was, less the first 10 feet, which is 0.4. No, I got to take.
Yeah, you got to take it off.
I got to take it off here. We're only using.
0.4. Less.
I got an easier way. See, this is where you get screwed up. We can show how much we need and how much they put in. Let's try it that way. I think that'd be easier.
Yeah.
They have put in a factory charge, which would have been 0.4 times 25, and that would have been 10 ounces. They put in 10 ounces, correct?
Right.
They put in 10. But we need 15 times 0.6 times 15, and that equals 3, correct? They gave us 10, but we only need 3. Is that correct? That's just a way of doing it without trying to screw up the math here. So if they gave us 10, we need 3. So we need 3. That leaves us with what? Minus 7? Is that correct?
Yes, but now we have to actually be 2.
We doing this right? Right, now hold on. They gave us 10, and we need 0.6 times 15 because we're using 3/8. So we need 3 ounces. That ain't right.
No, that's 9.
9.
Yeah.
I was testing you, Kevin, and you passed. Duh. Okay, it's 9. So we need 9, but they gave us 10.
Take 1 ounce out.
So that's less 1, right?
Right.
Isn't that correct?
Right.
So now that brings us down to 50.7. See, that's what happens. You stand up here in front of a transparency with a camera and a million people watching you.
50.3.
Huh?
50.3.
Well, you're too quick. What did we get to 0.3?
51.3 minus 1.
Yeah.
It's a 7.
It's 50 point,
Oh, it's a
that's
7.
a 7. I said I'm in front of a transparency with a million people watching me. Anyhow, 50.7. But, tell them, Ray,
Got to add for the dryer.
dryer. Excellent.
8.1.
So now we have to add 8.1. But this is good, see, because you have a lecture on video that's like a class. The same things happen in a class. 8, 8, 5. Point is, we can still figure it out. So the math all looks good here. Only trying to show you a shorter one. So you may think sometimes that you have to recover, but you really don't, because the dryer is what really adds it again, and you're already using larger typically. But even if you have to recover, so what? Are we okay with that?
Yes.
Let me give you an example. Let's just say you had to recover. Let's just say as an example, let's say you needed 60.2 and you had 62.4 in the system. This is what you need. And the system was already charged with 62.4. So you'd have 2.2 ounces too much in there, correct? How are you going to recover 2.2 ounces?
Just leave it in.
Why?
You got your 2 ounces. Plus
Exactly. Plus or minus 2 ounces, leave it alone, you're done. Go home. Right. Or, well, you could put it in a hose. A hose could hold, it's a 1/4-inch hose typically, 0.3 ounces per foot, 5-foot hose, 1.5 ounces. It would be a de minimis release, legal, de minimis release, because it's in the hose. You don't want to make that a common practice, and it doesn't happen, because typically you're going to be adding, okay?
Yes.
All right. We okay with that? All right. Almost done. Have to get through all that, and that's the most difficult. Now, so let's see, I think we've covered that. One thing that I want to stress, and that is when I gave you this PT chart, which is in the book, again, it's for R22 and R410A. There are, I'll just go back over here. There are many different classes today on R410A. We have done classes that took 4 hours. We've also done classes that take 10 minutes. So how about if I give you a class on R410A now that'll take 30 seconds? How's that? And you'll know exactly what to do. Because the fact is, ladies and gentlemen, R410A, all the rules are identical. They're the same. The only thing you have to worry about is that all the pressures are 60% higher. All you do is plug in higher numbers. You have to have R410A equipment, a recovery manifold, and that would be about it. Of course, your dryers today are for 410A. But all the service procedures, superheat, subcooling, everything that we talked about is the same, but 60% higher. So now you're certified in 410A, right? But again, you can make an all-day seminar out of 410A. And the point is, you have to be careful with it. It's not a joke. And of course, I don't mean to make light of it. But the point is, you have to be careful. You need to be wearing your goggles today, even if you were very lax before with 22, because the pressures can hurt you today. You break a line, it's going to be a problem. Just keep in mind, 60% is quite a bit higher. Okay? You got any questions on that? Okay. We're winding down. I got one more thing to do with you now. And let's go to page 10. And on your page 10, ladies and gentlemen, is the job site sheet. So on the job site sheet, I'll be right there. The job site sheet is similar to the heating one. Air conditioning, again, the owner, service contractor, model number, outdoor unit, evaporator, serial numbers, all the different actions that you've took. you really don't have to stress that so much, but I'd like you to go over to the very next page, and you'll find this. Now that's on your page 11. Isn't that 11?
Yes.
Okay. This is a job site sheet designed by Reed. And it's fine. If you really like this, this works very well. Before, when we did our examples, we were doing a clockwise version of a refrigeration system. When you do this one, it's counterclockwise, but it doesn't mean any difference. It's just a method for you to be able to write down the data. You could actually draw pictures like this and fill them in and give us the information. But in case you have to fax this, we'd like you to follow the guidelines. And it says, and again, very busy. We've got a compressor, we've got a condenser, liquid line, evaporator, suction line. Let me give you an example. And when we're done with this, we're finished. It says circle the metering device used. Well, if we come down to the metering device, we know the metering device is before the evaporator. And so let's say we would circle fixed for an orifice. Then it says circle yes or no at dryer locations. Now watch this one. We know that after the condenser, we have a liquid line. Well, they're showing either a dryer here or here. And we say, nope, we don't have a dryer here. And we don't have a dryer here. So does that mean we don't have a dryer? No, it doesn't mean we don't have a dryer, because our dryer is here. See? So in other words, we challenge them a little bit with this, and we say dryer. There's a reason why they do put that dryer up here, though, because on our high efficiency units, ladies and gentlemen, they put the dryer inside the cabinet of the AC unit. But keep in mind, it's still in a shade there. And the reason they put it out there is because it's an optional thing, costs more money. And it's better to have one dryer instead of no dryer. So we advise our customers that if it's a 12 SEER or higher with the dryer inside, of course you leave it there, but we also tell you to put one here. So we want you to use two dryers. Put one before the metering device so we get no debris in there, okay? However, keep in mind also that if it's a high efficiency unit, you're supposed to be using a TXV, but some contractors don't do that, okay? Now, then it says circle the service ports. Okay, well, we have a high side service port, and we have a low side service port. We're not using a low side dryer. Let's talk about that real quick, please. We only tell you to use a low side dryer today. If you have a burnout, you do not install a low side dryer for any other reason. However, for the past 2 years, we don't even tell you to do that anymore. Since our 11 has not been available, we could not flush anything out anymore. And the manufacturer suggested one of two things. Either change multiple low side dryers. You change the low side dryer and you go back and you check the oil for acid content. If it's still acidic, you change the dryer again. And that's very time consuming. Or they suggested changing the whole unit. But for the past couple of years now, we have a flushing agent that is available, and it works, and you use it identical to our 11. That's for another class. I just want to let you know that if you flush the units, if you cut everything apart and isolate them, flush your lines, flush your evaporator, you can back flush an evaporator, you flush your condenser, you are then able to, let's say, reinstall a new compressor with that, braze everything back in place, and you need no dryer. It comes out like brand new. That's the current technology, okay? All right. Let's go back and let's bring the job site sheet up again. And over here it says saturation temperature is pressure converted to temperature. So let's do that. And I'm only giving you this as an example. Let's put down our low side pressure. Let's say it was 68 psi. And our high side pressure, wasn't that 278? Yeah, 278. And so for superheat, the vapor line temperature, we said we had a suction line temperature of 50, and we had a saturation temperature of 40, and that gave us 10 degrees of superheat. Then on the high side, we had a saturation temperature of 125. We had the liquid line temperature of 110, and that equals subcooling of 15 degrees. Oh, I suppose a couple of other things we could fill in here. Outside temperature, we says, was 95. Over here is the vapor line temperature again, it's 50. Before we go into the compressor, do you notice that they have liquid line temperatures and vapor line temperatures in different places? If you were in trouble, we may ask you to do that. We may ask you to take temperatures in different areas. But the liquid line temperature that we were looking for would have been 110 right here. We also said the inside temperature, the supply would have been 60, and the entering, which is your return, would have been 80. So again, it's just giving you an idea. You can fill in line size and all the rest of that stuff. But this particular chart is the same as us doing this right here. Okay? But whatever method you use, you can draw your own picture, you can use the chart, you can make a drawing. Okay, any questions on this at this point? Okay, I will kill that. We're going to conclude here in just a few minutes. You find your own method to diagnose, find your own method to service. We make something very clear too at all of our classes. We say, and I don't know if I've mentioned this before, but as a technician, the technician works for a contractor. No matter what we say in class or what we recommend, the technician must always do as the contractor asks them to do, because it's the contractor that's paying the technician. We can advise and tell you what's recommended in class. You have to do what works for you. But again, we're doing all of this, so we've given you some technical information. We've given you a crash course in AC, how it is today. Given you methods on how you're able to help yourself, and also told you how to request some technical help from the Amico branches. So on that note, gentlemen, do you think we've covered this pretty well at this point? Again, this was the video that we had intended to make available. So we're okay with all of that. Jeff, are you clear on that? Mm-hmm. All right, then, ladies and gentlemen, we have concluded this part of the program. Well, again, we thank you very much for spending the time with us. Thanks.